Dr. R. Hemavati is an assistant professor in mathematics in Queen Mary's, Chennai. She has specialized on functional analysis. Having 12 years of experience in teaching, she has won various awards for her performance. She has published papers in 14 international journals, 3 national journals, and has presented papers in 10 international and in 5 national conferences. She is also one of the editors for an international journal.
Welcome to UGC lecture series. In earlier sessions, we have dealt with discrete distributions of binomial distribution and Poisson distribution. In this session, some more examples in Poisson distribution will be dealt, and next in line we will continue with discussing the discrete distribution with one more distribution called a geometric distribution. So, in this session some examples of Poisson distribution are worked out. Also, we are going to deal with geometric distribution concept in detail by discussing the mean, variance and MGF. Now, this is a problem where we have approximated the binomial distribution to a Poisson distribution. So, a binomial distribution will become Poisson distribution if n is very large and p is small. So, this is an example where the parameters of n and p are given and we are asked to find out the probability using Poisson approximation. So, take this, it is known that the probability of an item produced by a certain machine will be defective is 0.05, considered to be small, and if the produced items are sent to the market in packets of 20, so n is equal to 20, find the number of packets containing exactly, this is one part of the question, at least another part of the question, and at most 2 defective items in a consignment of 1000 packets using Poisson approximation to binomial distribution. So, for finding the number of packets, first of all we have to find out the probability that the packets exactly there are 2 defectives and at least 2 defectives and at most 2 defectives. 3 kinds of probabilities we must find and multiply that with the frequency, that is 1000 packets, we will get the number of packets containing exactly, at least and at most. Okay. We shall solve this problem. What is given in the question? We are given n and p value. So, using Poisson approximation, first of all we are given n is equal to 20 and p is equal to 0.05. What is the Poisson approximation to binomial distribution? Lambda is taking the value np. Okay. So, n is 20 and p is 0.05. So, lambda will become 1, right. So, lambda is 1. With this lambda value, we will proceed to find out the probability of exactly, what is the first question? We have to find the probability that the consignment consists of exactly 2 defective items. Number of packets containing exactly 2 defectives, in a consignment of 1000 packets. What is that equal to? So, capital N into P of x is equal to 2 and capital N is 1000 and P of x is equal to 2, we have got the answer 0.1839. When multiplied, this becomes 183.9. Because we want the number of packets, it should be 184, rounded off to the nearest number. Okay. So, the second question is find the number of packets containing at least 2 defectives. So, at least 2 defectives, mathematically it is represented as P of x greater than or equal to 2, and this is from P of 2 etc. up to infinity, or we shall write 1 minus P of x is equal to 0 plus P of x is equal to 1. Okay. So, it is 1 minus e power minus 1 by 0 factorial plus e power minus 1 by 1 factorial gives us the answer 0.2642. Then we have to find out the number of packets. Number of packets containing at least 2 defectives. that is equal to again capital N into P of x greater than or equal to 2. Capital N is 1000 into 0.2642. So, that is equal to 264.2 rounded off to the nearest number 264 packets. 264 packets contain at least 2 defectives in the consignment of 1000 packets. Okay. The third subdivision is you have to find out at most probability that there is at most 2 defectives. At most is represented as less than or equal to in mathematics. Okay. So, P of x less than or equal to 2 is P of x is equal to 0 plus P of x is equal to 1 plus P of x is equal to 2. Okay. So, this is e power minus 1 by 0 factorial plus e power minus 1 by 1 factorial plus e power minus 1 by 2 factorial. Okay. When substituted, this gives the answer 0.9197. Okay. Then we have to find out the number of packets containing at most 2 defectives. This is equal to n into P of x less than or equal to 2, and this is 1000 into 0.9197, and this is equal to 919.7, which is approximated to the nearest whole number as 920. So, the answers for the question is number of packets containing exactly 2 defectives is 184 and number of packets containing at least 2 defectives is 264, right, and number of packets containing at most 2 defectives is 920. So, we have done a problem where the Poisson approximation to binomial distribution was considered. Okay. Next is a problem which uses the additive property of Poisson distribution, that is, find the probability of 5 or more telephone calls arriving in a 9 minutes period in a college switchboard if the telephone calls that are received at the rate of 2 every 3 minutes. So, at the rate of 2 every 3 minutes is given, that is the mean rate of arrival is lambda is given to be equal to 2 and that is given for the particular 3 minutes only, whereas the question is for 9 minutes. So, 3 minutes period should be converted for 9 minutes period. How shall we get it? First of all, let us take x1 is a Poisson random variable following the Poisson distribution at the mean rate of 2 at first 3 minutes. Then you take the second 3 minutes. Second 3 minutes is also following the Poisson distribution at the rate of 2 for the second 3 minutes. What is the third 3 minutes? Third 3 minutes is also following Poisson distribution with parameter 2 and for a third 3 minutes. So, the first 3 minutes, second 3 minutes and third 3 minutes together added gives you the total 9 minutes period. For this 9 minutes period, we should find the probability of 5 or more telephone calls. So, how to do this problem? Okay. First of all, let us take x1. x1 is the number of telephone calls arrived in first 3 minutes. Then x1 follows a Poisson distribution with parameter lambda 1 and this is given to be equal to Poisson distribution of 2. 2 is the parameter, lambda 1 is equal to 2. Okay. Similarly, you take x2 is equal to number of telephone calls arrived in second 3 minutes. Okay. Then x2 is following Poisson distribution with parameter lambda 2 and this is also equal to P of 2 where lambda 2 is equal to 2, right, and x3 is equal to number of telephone calls arrived in third 3 minutes. So, x3 is following Poisson distribution with parameter lambda 3, that is also equal to P of 2, where lambda 3 is equal to 2. Totally x1 plus x2 plus x3 according to the additive property of Poisson distribution follows a Poisson distribution with parameter lambda 1 plus lambda 2 plus lambda 3. So, we have x1 plus x2 plus x3 denoting the number of telephone calls arrived in first 3 plus second 3 and third 3. So, arrived in it is 9 minutes, 3 plus 3 plus 3, 9 minutes period, arrived in 9 minutes period. So, that is following a Poisson distribution. So, x1 plus x2 plus x3 is following Poisson distribution with parameter 2 plus 2 plus 2, which is equal to Poisson distribution with parameter 6. So, this particular x equal to x1 plus x2 plus x3 following Poisson distribution with parameter 6 means lambda is equal to 6. Okay. And the question is find the probability of 5 or more telephone calls in a 9 minutes period. So, we have arrived at 9 minutes period and then we have to find out the probability of 5 or more telephone calls. Required probability is P of x greater than or equal to 5. Okay. So, first of all before this we shall write the probability function. P of x is equal to x is e power minus lambda power x by x factorial. Lambda is being 6. So, e power minus 6 power x by x factorial. X greater than or equal to 5, it becomes P of 5 plus P of 6 probability. Here this P represents a probability plus etcetera up to infinity. Okay. Or it is written as 1 minus P of x less than or equal to 4. Okay, which is 1 minus P of x is equal to 0 plus P of x is equal to 1 plus P of x is equal to 2 plus P of x is equal to 3 plus P of x is equal to 4. Okay. Substituting the values e power minus 6 power 0 by 0 factorial plus e power minus 6 power 1 by 1 factorial plus etcetera e power minus 6 power 4 by 4 factorial, we get 1 minus what is the respective answer 0.0025 plus 0.0149 plus 0.0446 plus 0.0892 plus 0.1339 and the answer is 1 minus 0.2851 and this is equal to 0.7149. This is the required answer, that is the probability of 5 or more telephone calls arriving in a 9 minutes period when the rate is given only for 3 minutes period. We have used the additive property of Poisson distribution and we have arrived at this answer 0.7149. Let us have a break. Welcome after the break. Earlier to the break we have seen a problem where the additive property of Poisson distribution was used and the Poisson distribution as a limiting case of binomial distribution was used. And the next is a problem where we find the conditional distribution of x given a value of x plus y is a binomial distribution where x and y are following Poisson distribution and they are independent. If x and y are independent Poisson random variables, show that conditional distribution of x given the value of x plus y is a binomial distribution. So, first of all we shall take the x and y as Poisson distributions and they are independent. Here x is a Poisson distribution with parameter lambda 1 and y is also a Poisson distribution with parameter lambda 2. What is asked? The conditional distribution of x given x plus y. Okay. So, the conditional distribution of x given x plus y is given some value as n. This particular probability we show that it is following the binomial distribution. So, we should arrive at a binomial distribution probability function. Earlier in the previous sessions we have taken the binomial distributions probability function and we arrived at Poisson distributions probability function. This is reverse, where we are taking the Poisson distribution probability functions and we are going to arrive at binomial distributions probability function. Using the conditional probability definition, we already know P of A given B is equal to P of A intersection B divided by P of B, right. Using this we shall have here, this is equal to P of x is equal to R is a one function intersection x plus y is equal to n divided by, this is B, x plus y is equal to n is called a B, is an event called B, P of x plus y is equal to n. Now, already x is equal to R can be substituted here and that can be brought to the next side. So, y is equal to n minus R. So, this becomes P of x is equal to R intersection y is equal to n minus R, x is being substituted as R and that is taken to the other side, okay, by P of x plus y is equal to n. Again for the denominator we are going to use the additive property of Poisson distribution, and here x and y are independent, therefore, P of A intersection B is equal to P of A into P of B. We can write this as P of x is equal to R into P of y is equal to n minus R. This is since x and y are independent, right, divided by P of x plus y is equal to n, and P of x is equal to R and P of y is equal to n minus R. We shall substitute the respective probability functions, and x plus y is equal to n. Since x follows Poisson distribution with parameter lambda 1 and y follows Poisson distribution with parameter lambda 2, by additive property x plus y will follow Poisson distribution with parameter lambda 1 plus lambda 2. Accordingly, we will distribute the probability functions. For this we shall have e power minus lambda 1 power r by r factorial, and for this e power minus lambda 2 power n minus r by n minus r factorial, and for this x plus y is equal to n, which is having the Poisson distribution with parameter lambda 1 plus lambda 2. Okay. So, this is e power minus lambda 1 plus lambda 2 into lambda 1 plus lambda 2 whole power n by n factorial. This is the main denominator, right. So, how shall we write this? N factorial goes to the numerator and e power minus lambda 1 gets cancelled with this particular e power minus lambda 1 and lambda 2, and combining this lambda 1 power r with this, and this is added and subtracted with r. So, we can write this as n factorial by r factorial into n minus r factorial, and this becomes lambda 1 by lambda 1 plus lambda 2 whole power r, okay, and lambda 2 by lambda 1 plus lambda 2 whole power n minus r. The whole power n which was splitted as n minus r for this and which is splitted as lambda 1 plus lambda 2 whole power r for this, okay. And if you take this particular thing as p, and this is actually giving you the NCR, okay, and p power r, if lambda 1 by lambda 1 plus lambda 2 is taken as p, and then automatically this becomes q power n minus r, where p is equal to lambda 1 by lambda 1 plus lambda 2. then automatically q will become 1 minus p and that will become lambda 2 by lambda 1 plus lambda 2. We arrived at which is PMF of binomial distribution. So, we got binomial distribution. Hence, we have proved the conditional distribution of x given x plus y becomes a binomial distribution. Next, fit a Poisson distribution for the following data. Okay. So, we have to fit a Poisson distribution for this particular data. How to fit a Poisson distribution? First of all, we have to get the Poisson frequencies. For fixing Poisson frequency, we need the parameter lambda, and for finding the lambda, we must find the mean for this frequency data. How to find out the mean for the frequency data? It is summation f x by summation f. So, first tabular column you have to form with the summation f x being found out, and then we have to use that to find lambda. After lambda is found, form another table with x and probability of x using e power minus lambda lambda power x by x factorial. Multiply those probabilities with the frequency total capital N, and that is the expected frequencies. That is how Poisson distribution is fitted to find mean, that is our lambda, then only we can proceed inside. So, x values are given 0, 1, 2, 3, 4, 5 and corresponding frequency values are given 142, 156, 69, 27, 5, 1. We shall do it here itself. F x we will find out 0, 156, 138, 81, 20 and 5. And this particular this thing gives you the total sigma f x is equal to 400 and sigma f is equal to 400. So, mean is equal to lambda is equal to sigma f x by sigma f is equal to 400 by 400, which is equal to 1. So, now we have found out the parameter lambda, lambda is equal to 1. Next tabular column to find the Poisson frequencies, to find Poisson frequencies. Okay. What are the x values? 0, 1, 2, 3, 4, 5 and Poisson values are p of x is equal to x is e power minus lambda lambda power x by x factorial. Okay. This is actually e power minus 1 power x by x factorial. So, e power minus 1 power 0 by 0 factorial. Likewise, you have to find out for this e power minus 1 power 1 by 1 factorial. Likewise, we have to find out and these particular values expected, these particular probability values has to be multiplied with capital N. What is our capital N? Capital N is sigma f. Okay. Sigma f is 400 into p of x, and these values are found to be 147.15. For corresponding to this, what is again 147.15, 73.58, 24.53, 6.13, 1.23. All these has to be rounded off, so that this total also gives you 400, because the observed frequency given in the question is 400, means the total expected calculated frequencies total also should tally with the given total. Okay. So, this is 147, 74, 25, 6, then 1. So, these are the expected frequencies. So far we have dealt with the Poisson distribution. In this session, we have dealt with examples of Poisson distribution using the limiting case Poisson distribution as a limiting case of binomial distribution, and using additive property of Poisson distribution we have dealt with one problem. Also, the Poisson distribution was fit for a frequency data. Okay. Based on the discussion, these are some of the exercises do on its own. If the number of telephone calls coming into telephone exchange between 9 am and 10 am and between 10 am and 11 am are independent and follow Poisson distribution with parameters 2 and 6 respectively. That is, number of telephone calls between 9 and 10 is following Poisson distribution with parameter 2 and between 10 and 11 following the Poisson distribution with parameter 6. So, 9 to 10 is separate and 10 to 11 is separate. Then you are asked to find the probability that more than 5 calls come between 9 am and 11 am. So, 9 am and 11 am is together of 9 to 10 and 10 to 11. So, if you take 9 to 10 as x and 10 to 11 as y, then 9 and 11 becomes x plus y. You are asked to find out p of x plus y greater than or equal to 5. Use the additive property, x follows p of 2, y follows p of 6. So, x plus y will follow p of 8. Using the parameter lambda is equal to 8, find the probability of more than 5 calls between 9 and 11. Okay. And this is another example where you can fit a Poisson distribution using the lambda. Lambda is found out as summation f x by summation f, and then find out lambda and you find out the respective probabilities, multiply it with the capital N is sigma f, you can find out the Poisson frequencies. Thank you.